Hello, welcome to my presentation on the cybersecurity body of knowledge, more specifically on the hardware security topic. My name is Ingrid Verbouwede and I'm from a research group COSIC at the KU Leuven in Belgium. Here you see the outline of my presentation. First, I will try to explain what I mean with secure hardware. We need secure hardware both at the cloud down to the most little devices in an IoT, Internet of Things component. Then I will define what I mean with a root of trust. We need that during our presentation. Then I'll explain what the design methodology is for designing secure hardware. And then I'll walk you through different hardware design abstraction layers, give examples, and at the end I'll have some conclusions. To start, I first want to explain to you what I mean with a next generation embedded system, and more specifically what I mean with a cyber-physical system. Cyber-physical systems, part of the cybersecurity we're trying to protect here. Here you see a typical cyber-physical system. It's a car with huge amount of components. Current day cars have probably more than 100 microcontrollers. And what's important in a cyber-physical system is that you consider networked. These devices are networked, all these processors. They're embedded, so they're inside, in this case, the car, and they interact with the environment. Those three components have to be present: networked, embedded, and interacting with the environment. And as you all probably know, these devices are being attacked. Here I show a dashboard picture, and the car is at full speed, more than 100 miles an hour. At the same time, it's stand at park. So someone played with the software. Attacks are possible on these cyber-physical systems. There's many more examples. You've probably seen them in previous lectures. Here you see a generic picture of a cyber-physical system. All components are present. Typically, at the center, we have what we call the infrastructural core. It's also called the cloud. You have large servers, huge systems, and they need what's called long-term terabits, long-lasting security, gigabits or terabits throughput and quantities. Next, around this is what's called the mobile access or edge computing. They're all the devices. They're probably rechargeable. You can plug them in the wall to recharge, but they're mobile. Examples are your smartphones or portables, things like that. They need megabits, medium range security. But at the edge, you have what's called the sensory swarm. All the lightweight, hardware-entangled devices, they also need security. And that's a challenge for the hardware designers to add security to these tiny devices. They often don't even have a battery, still they need security. Examples are maybe medical implants, IoT devices, smart meters, all these little devices. So in general, anything which starts with E these days, e-health, e-commerce, e-voting, or smart grid, smart home, smartphone, smart car, they will need security. And in general, we can say anything that starts with an E or a smart will not be possible without security. The problem or the design challenge for the hardware designer is that we want to provide security and privacy, but within the area, the time, the power, and the energy budgets. And that's the challenge. We want to co-optimize these parameters together with security. But before I start to explain on how we do that, I want to explain to you what for hardware design is important as trust and trust boundaries. And for that, I'll go back to the basic definitions. One definition is one that I found by Ross Anderson in his book on security engineering. He has it after the NSA. And he says that a trusted system or a component is one whose failure can break the security policy, while a trustworthy system or component is one that won't fail. Now, we often in hardware, we do have some component, and we call it a root of trust, that we need to trust without sometimes having a confidence of it being even trustworthy. Another definition, which comes from the trusted computing group, is that an entity can be trusted if it always behaves in the expected manner for the intended purpose, which for our purpose, loosely stated, means if a trusted system or component fails, then bad things can happen. And the goal of security, and certainly of hardware security, is to minimize what needs to be trust. And that's why we introduce roots of trust. Now, these roots of trust have changed over time. And I will start with what I'll call the old model, trust boundaries in the old model. In the old days, people had PCs on their desk, computers were sitting in server rooms, and what needed protection, security protection, was the communication link between those two. Now, the communication link is what's being attacked, so that's the arrow what you see here. So I have my PC here, I have my server here. So we assume that the attack sits on this communicating channel. Now, we also therefore assume that the actual encryption and the cryptographic operation sits in black boxes, in these boxes. Now, to protect this link, we need strong mathematical algorithms and protocols. And to implement those, we then assume, and we're going to focus on efficient implementation of these crypto algorithms. Efficient meaning that they fit in the power, the area budget, and so on. So in the old days, what we would make hardware security components which were fitting in the area budget, probably in the time budget. Very important there, different throughput requirements, but also important is the power and energy budget. And then later on, physical security requirements were added, and of course all of this needs to be done within cost budget of development budget, which is called a non-recurring engineering cost. What I will do now is very shortly explain each of these requirements and how we measure them, and then we'll go to implementations. So how do we measure area for a hardware designer? We can make ASICs, and these are dedicated, what's called application-specific integrated circuits, and there we're going to count transistors. Transistors actually and gates. Gates are built out of transistors, like here. This is a typical NAND gate. This would be the layout of the NAND gate. And in ASIC design, we count the number of gates that we need to implement the circuit. Another platform that a hardware designer will use is an FPGA. It's a field programmable gate array, and there we measure the cost by its units, which are typically the lookup tables and the amount of memory, specifically block RAMs, that are used to implement our security target. We also implement often on embedded microcontrollers. These are small microcontrollers, and there our cost is measured by the program size and data size that we need for our implementation. If you go to larger systems, microprocessors, system on chips, multi-core, cloud platforms, then we're going to count the number of cores, the memory side, and so on. This is the first cost that we have, that's the area cost. Now these days transistors become cheaper, and most of the time we're kind of fitting the area cost. That's not an issue. The second requirement for our implementation is that we need to finish, or we have a time budget. And that can be the sample frequency, the throughput, the latency, things like that. So what do we measure? Many applications put a constraint and say that we want a minimum amount of throughput. Throughput is a property which is associated with an application. So this is the amount of data we can process per time unit. For instance, in video, this would be gigabits per second. If this is internet, it would be gigapackets per second, and so on. So we want the hardware to work as fast as possible, as fast at least that the application requires. If you go too fast, I mean, maybe your processor will be idle for a while, but that's the minimum requirement. Another requirement, which is often forgotten, is actually requirement for latency. Again, latency is a property which is associated with the application. And it actually measures the delay from input to output, or the reaction speed turnaround time. For instance, the brakes of a car. If a situation, or you notice a situation, a sensor of a car measures that an event is happening and that you need to brake. If you want to measure that this sensor input is authentic, you need to add crypto, but you have a real time or a latency requirement in the sense that you want to react as fast as possible. The same happens actually on systems on chip, where you want to do very low latent memory encryption. Now, often in many implementations, high throughput, low latency don't go together, because for high throughput, we use pipelining, and pipelining actually increases the latency. Now, that's a hardware challenge that needs to be addressed. So one example, so in the past, we would just go for efficiency. We want to be fast, and we want to be low latent, and we want small area. And the old days, we would implement the most well-known algorithm being the data encryption standard, the DES algorithm. You see an example of that here. This is the layout of it. And if we build coprocessors for these things at that time, we would look at this thing being able to do encryption or decryption, triple DES, pseudo-random number generation, MAC generations, modes of operations, things like that. This was the first focus. And then the second topic which need to be addressed, or the second challenge, is actually power and energy. Because in many applications, the power is limited. We look at an RFID tag, it doesn't even have a battery. If you look at, in this case, cool infrastructure, this is the cool infrastructure of the server rooms of server infrastructure of well-known US company. Look only at the colors. These things need cooling, a huge fortune this costs. Another example of cooling is implantable devices. If we don't want a device to heat up, the temperature can only raise with 1 degree Celsius. It means that you need to really operate low power. A second requirement, which is related but which is not the same, is the energy consumption. Many implantable devices have small non-rechargeable batteries. So here is an example. This is a pacemaker. A pacemaker has a non-rechargeable battery, and so if you want to add security or you want to add crypto to it, you don't want the battery to die quickly. So you don't want the patients to go back every 6 months because crypto has consumed too much energy. And in that context, for instance, Bitcoin mining is hugely energy consuming. It's, in my opinion, even ecological disaster, but that's just a side note. So one of an important optimization goal of a hardware designer that wants to implement security is how much crypto can we get out of 1 joule or 1 microjoule. So here I show another example. Randall or AES is an algorithm that we want to implement. We want this to be low power, high throughput, and so this is a typical ASIC design based out of standard cells. It gets a throughput of more than 2 gigabits per second, but what's important, it consumes only 56 milliwatt and will give you 11 gigabits per joule. And gigabits per joule is a nice target, is a metric to compare the efficiency of your designs. The hardware designer also has a choice of digital platforms. And here you see a list of possible hardware target platforms for the same crypto algorithm. And this is the AES algorithm, 128-bit key, 128-bit data. And what do we want to do is we want to implement it on many different platforms. And for each of them, we want to measure the throughput, and we want to measure its energy efficiency. The energy efficiency, which is gigabits per second per watt, is actually gigabits per joule. We cannot directly measure this, so we measure the throughput, we measure the power consumption, and we'll divide both. We're going to get the gigabits per joule. The first was this ASIC chip that I showed you. It's dedicated to encrypting AES, and it reaches 3.85 gigabits per second. at a cost of 350 milliwatts. On FPGA, we can also implement AES. It gets you slightly lower gigabits per second because this is a programmable platform. It's not a dedicated platform, but still at very good quality power consumption of close to 500 milliwatts. You can use these days high-end processors like the Intel processors, x86 processors now have native instructions to support AES. These are dedicated instructions just to implement the AES algorithm. These processors, or most fancy technology, gives you 30 gigabits or more. This is already a little bit older estimate, and results in 32 gigabits per second. This is the fastest of the whole list. But it comes at a cost. The cost is 95 watts. So this is not a typing mistake. This is the actual power consumption of these processors. So you get the fastest, but you're absolutely not lower power. And so on. We can say we see this is an assembly optimized implementation on a low power processor, but still gets 31 milliwatts. An assembly optimization on a Pentium processor that does not have the native instructions, so the throughput is going to be reduced. And then those are, and I added those because these are extremely low power processors. Low power processors, but they get extremely slow throughputs, only 133 kilobits, or in this case, even 450 bits. Because this is a Java running on this embedded Spark. This is a Java implementation. Now, when we look then at the figure of merit, what you see is that for one and the same algorithm, the gigabits per joules can differ orders of magnitude. If you have a dedicated ASIC, you get 11 gigabits per joule. FPGA, you lose some, around 3 gigabits per joule. This Intel processor is extremely fast, but it consumes a lot, so you lose, you're only 1/33 part of it, and so on. And you see that choosing a low power processor doesn't necessarily give you energy efficiency. This is 5 orders of magnitude, and this is 7 orders of magnitude different compared to my dedicated. And the reason is that these platforms, both hardware and software, were never built with security in mind. So it's important to focus on efficiency. And then what's coming on top of it now is that we want to add not just being efficient, we want this implementation also to be secure. Here you see what we consider now the trust boundaries, or the current model of it. We have many devices, IoT devices that talk to mobile devices, that talk to each other, and so on. And the trust model we assume now is that we have attacks not just on this communicating channel, but also on the endpoints, which means that my encryption and cryptographic operations no longer sit in black boxes, but they sit in gray boxes. We still use protection by strong mathematical algorithms and protocols, but we also now need secure implementations, not just efficient implementation, but also secure implementations. I showed one example here. This is an implementation from a very secure elliptic curve implementation on an FPGA. This was a master thesis project, and what you can see is that with a loop antenna, we can actually pick up what the chip is calculating on. So this is a typical physical attack. It's an electromagnetic attack on an unprotected implementation, and I'll show you later on why, how this can be fixed and what's the source of this problem. And what you see is that out of when you pick this is what the antenna picks up, and what you see is that the distance between the peaks tells me actually what calculations are happening and whether the key bit was 0 or 1. The key bit is 0, less calculations need to be done, then when the key bit is 1, and only by measuring the distance between the peaks I can read out the key. So I can choose a secure algorithm, I can make an efficient implementation, but if the implementation itself is not secure, I still have security problems. I don't have a secure implementation. So for my cyber-physical systems, I actually need both. I need very efficient, lightweight implementations, which are within the power, the area, timing budgets. And it might be a challenge to get this working on a passive RFID tag or on this tiny microcontroller. Certainly if you use old-fashioned public key, like 1,000 or 2,000 or 4,000 bits RSA. And on top of that, the efficiency, I want trustworthy implementations. These implementations should be resistant to attacks, active attacks, probing attacks, power glitches, JTAG, scan chain inputs, and so on, and passive attacks like sidechannel attacks, power, timing, electromagnetic, and these days also microarchitectural sidechannel attacks. So now that I have explained to you that we need efficient implementations, secure implementations, we want them to be low power and we want them to be secure, how do we approach this problem? And here we go actually to the core of this body of knowledge on hardware securities. What are the design methods to give me this low power, low energy, high security implementations? And in hardware design, what we do for that is we actually split our design in multiple design abstraction levels. We typically start by investigating the application. This could be something from e-commerce, smart energy, whatever. We therefore then decide what is the required security protocol. Do we need authentication? Do we need privacy? Do we need remote authentication? What are the topics we want to protect? Now, these security protocols requires efficient implementations of crypto algorithms. We choose the right algorithms, crypto, entity authentication, and so on. For that, we have to choose the right architectures, and the architectures can be hardware, software, co-design, maybe a system on chip. These architectures require microarchitecture details, probably also protection against microarchitectural attacks. Maybe we have to design some co-processor. And at the bottom, we actually have to worry about the right circuit techniques, maybe to combat sidechannel attacks, maybe to include a nice puff or random numbers. And why do we do that? Because we want to get this low power, low energy, but also we want it to be secure. And we can choose very strong crypto algorithm, but if the implementation leaks, then we have a problem. The key might leak out or the data might leak out. Same if we have a strong protocol, but we choose a weak algorithm or we choose a weak software implementation, we might have an issue. And that brings me back, actually closes the loop with this root of trust, which we want at each level. An application engineer might say, okay, my root of trust is my trusted platform module, a TPM. But the designer of a TPM is going to say, what do I need to trust inside my TPM? Can I get this thing lightweight? I cannot add a TPM to every and each IoT device. This by itself requires that the TPM will rely on this. The root of trust for it might be the selection of the correct crypto algorithms. Now, the crypto designers, they assume that they have secure implementations. And the secure implementation guys assume that they have secure technology. Maybe they rely on puffs, secure key storage, random numbers, and so on. So the definition of a root of trust is a component at a lower abstraction layer upon which the system relies for its security. So from top to bottom, we go down in the abstraction layers, and if you design at a certain layer, your root of trust will be one layer down. And it's this root of trust, one layer down, which we're trying to design. And these are the different abstraction layers that the hardware security person and also the body of knowledge will consist of. And what I will do now for the remaining of the slides is that I will look at each of these abstraction layers and just give some examples. So we want to know what is the body of knowledge at the different abstraction layers. And these are illustrations. If you want more formal definitions, more examples, you should go and see the document. So at the top, we talk about secure platforms. This is the highest abstraction level for hardware from a hardware perspective, and what is visible to the software designer or security protocol designer. That's what he's going to be based or consider his root of trust. There are some examples here. A hardware security module or an HSM is a root of trust for many applications. On other applications, it's called a secure element or a smart card. And then still other application, it's called a trusted platform module, or TPM. Now, for hardware designers, those by themselves are very complex systems. And I show you one here, and the one that I want to show is a smart card, because I have a nice picture of it. This by itself is a complicated system. As you can see, it's a dedicated semiconductor-based device component. It's used in your phone, just like the SIM card of your phone, or the smart cards like identity cards, bank cards, and so on. It typically will have multiple types of memory, ROM, RAM, EEPROM, flash. It will also contain the CPU. It will have a set of crypto accelerations, and it will have lots of physical countermeasures. Now, this is a complex system to design, but for the application engineer, this will be his root of trust. If I go one level down on these processors, whether it's in TPM or it's in the hardware or it's on the smart card, we want support for software security. There is a separate body of knowledge on cybersecurity which deals with the software security side. They often assume that I have a processor that gives me hardware features to support basic operations, as I want isolation, I want attestation, I want authentication. How can hardware support that at a software level? In general, this is called the concept of a TEE, or a Trusted Execution Environment. Again, there is many examples of that. ARM Trust Zone is one, Intel SGX is one, or one that we developed at K11, which is called Sancus. And as an illustration, I will use that one, because for the other ones, I might not have sufficient amount of pictures. So here you see one such example. What we want to do is actually, we want to modify the processor architecture to support some of these security features. And in this case, we took an open source embedded microcontroller, which is called the MSP430. And the modification is that now we make sure that the memory access are under control. And it's actually program counter-based access control. So you cannot jump from anywhere in your protected memory sections. It's based on the position and the value of the program counter. It comes with a dedicated set of instructions. You see a nice picture here, is that if this is my total memory, it will be subdivided in sections which are protected. And this is the text section which is protected. This is the data section which is protected. And you can have multiple of these sections, and each of them will have their own metadata, storage keys, and so on. And no further details on this one. If I go one level down, these secure platforms, they do require quality implementations of the cryptographic algorithms. I have shown some of you in previous slides, like the DES implementation or the AES implementations. And in general, we want implementations of broad categories of algorithms. Secret key algorithms like AES or triple DES, or now new lightweight authenticated encryption schemes, which were developed in the CSER competition. There is recently a new NIST call for lightweight encryption. You have public key algorithms, like the old-fashioned RSA. There's many variations of the elliptic curves. There's also a large set of hash functions that needs implementation, like the SHA-3 and so on. And these days, people are also looking at post-quantum algorithms that need implementations. We want all of them. Of course, again, we want them to be compact. We want them to be low power, low energy, and with protections against attacks. One example, this is an elliptic curve public key coprocessor for RFID, which can calculate the core operation of ECC, which is a point multiplication, quite fast. I mean, it's kind of on the slow side, 5 microjoules. But it has hardware, it's hardware software co-design. It has a power budget which fits in a passive RFID tag together with a suitable set of sidechannel attack countermeasures. This is one example. You go to different applications, you want memory encryptions, you want low latency, very compact, lightweight versions. You want post-quantum, you need very efficient implementations of lattice-based crypto, and so on. If you want cloud encryption, you want throughput. So a trend which just has started, and I think a lot of body of knowledge will appear in the coming years, is actually implementations for post-quantum. What is this post-quantum? This is actually the idea is that if quantum computers appear and nations and large companies are working on it, then the current generation of algorithms, being RSA or ECC, their security will fail. So the mathematical foundations of existing public key algorithms will disappear. And so these novel post-quantum secure public key algorithms, most of them will be, or lattice-based schemes are very popular, seems to be in the crypto community. One example is shown here. It's called the shortest vector problem. You want to figure out in this lattice which is the shortest lattice point to a certain element. Now for these algorithms, we want new algorithms. They need to be efficient. They need to be sidechannel attack resistant. Again, and they need to be post-quantum secure. So it's an added requirement. Now the efficiency is still on existing computers, existing hardware, existing platforms. We want them to be secure. So we want these algorithms to be efficient, secure on our, and so we need to develop new hardware architectures. Then we go one level down. One level down is what I call sidechannel attacks. That's really at the microarchitecture level and at the circuit level. And in sidechannel attacks, there are a few major categories. One is the microarchitectural sidechannel attacks. Examples are Spectre, Meltdown, Foreshadow. And they abuse the fact that computer architectures are optimized for performance, but they're not optimized for security. Performance optimizations of computer architectures are, for instance, branch predictions, cache architectures, and so on. The second category in this sidechannel attacks are what's called physical sidechannel attacks, like power, timing, electromagnetic attacks. What you do there is, instead of abusing this performance optimization features, you're going to measure the power consumption of a small device or a bigger device, and from the power consumption you will learn information about what's actually being implemented on the device. Examples are, for instance, if you multiply with a large number, you're going to consume more power, you're going to need also more time, and this information you can use. And then there is a large category of active attacks. One example is, for instance, lasers, but you could also manipulate with the power supply. You can play with the clock, and you can heat up a chip. What happens if you heat it up? Does it still consume? Does it still perform the right operations, and so on? So this is what a slide which I showed before is the one which has these attacks based on electromagnetic. So it sits in this level 4 category. And now I want to explain to you why do you see this difference happening. And you see this difference happening, and I want to illustrate that here with this timing attack. This is the top level view of a what's called elliptic curve public key point multiplication algorithm. It's a top level description. So as input you have a public point P, but you have a secret key K. And this secret key is W bits wide. And the output is going to be K times this point P, so point P added by itself K times. Now how does the algorithm work? It actually goes to each of the bits of K, starting by the LSB, and if the key bit is 0, you only do the double operation, but if the key bit is 1, besides the double, you'd also perform a point addition operation, and then you keep going in this loop W times. Now if I show this on the flow chart, you check if you're smaller than the boundary, if you will double this operation each time, but then you check the key bit, and you can see that the calculations for key bit is 1 are much longer than key bit is 0. And this is called a timing side channel. Timing side channels are also the basis for cache timing attacks. In this case, we could actually relatively easily solve this by adding dummy operations on the right branch. Now, simply adding dummy operations might lead to other attacks, and a clever compiler will actually remove our dummy operations again. So often design tools are against optimizations that we want for security, not for performance. Of course, if you add dummy operations, you're going to need extra energy, extra power consumption, and that's also maybe something we don't want. Which actually brings me to the fifth level, and that's adding countermeasures for these attacks. And in general, at circuit level, also at architecture level, we see two major categories of countermeasures. One category is what we call hiding. We want to make the power consumption variations independent of the data being processed. This can be done by circuit styles, such as dynamic differential circuit styles, balanced place and route techniques. Most well-known examples are sense amplifier-based logic, wave dynamic differential logic, and so on. Many derivatives of this exist. And the other one is randomization or masking. You can add randomization at algorithm level. For instance, that's done by public key. That's also done, masking is also applied to some of these post-quantum schemes. You can also do circuit level randomization, and then it's called mask logic styles. There's other techniques based on secret sharing or on multi-party computation. Now, in each of these cases, you will need some source of randomness on chip. And so what you see, if you use this kind of countermeasures, your one level down, or the root of trust at that moment, is going to be your random number generator on chip. Here I show again one example. This is the cost you have to pay, or the price you have to pay for an AES implementation to make it secure. This is an insecure chip. This is a secure version. So the regular version, the insecure version, will give you 1 gigabit per second. 3.8 gigabits per second at 330 megahertz. The slower version is the one with protection. And so the protected version consumes 200 milliwatt, unprotected only 50 milliwatts. You see that to add protection, you pay a price. Throughput goes down and the power consumption goes up. Now, a clever designer will limit these protections or to the parts of the chip that need protection. So often in a large system on chip, many parts don't need, and you need to isolate or you need to confine the parts that need protection. So then the cost can be actually reduced. Which brings me to my lowest level, close to the transistors and the technology. And there I want to illustrate this with two body of knowledge topics. And one is called PUFs, physically unclonable function, and the other is called TRNGs, or true random number generators. PUFs have been promised as a replacement for key storage. They're also being promised as a cheap alternative for IC authentication. Random numbers are used for key generation, nonsense, to introduce freshness in your design, for instance, to apply for the masking schemes, and so on. Let me first introduce to you what I mean with PUFs. In PUFs, we want to use the silicon variability. PUFs are the silicon biometrics, and we use variability in transistors, in interconnect. Usually when people make chips, these PUFs, these variations are not required. Examples, for instance, these random dopant fluctuations or line edges. You see here, these lines are not perfect, they're a little rough. And it becomes worse when you scale down, and that's related to what's called Pelgram's law, which says that the variability goes up as the W, which is the width, and the length of the transistors goes down. And here you see a 3D picture of such a transistor with the width in this direction, the length in this direction. There's a lot of variability there. Protocol designers, crypto designers, they rely, or for them, a root of trust would be this ideal PUF. What is an ideal PUF? An ideal PUF is an integrated circuit which has a very large, what's called challenge response space. So you apply a challenge, you'll get a unique response. You apply the same challenge to a different PUF, you're going to get a 50% typically Hamming distance. Those two should be statistically different. You apply a different challenge, you should get again a unique response, and here again its own response. So this ideal PUF is a circuit which has a large, what's called challenge response space. It's a chip-dependent binary function. In reality, we're going to get some noise. Each time we read a chip, we're going to have a small variation. Typically, there is 1 to 15 to 20% noise on these readings. If I do the same to my second chip, you're also going to get some noisy readings. An ideal PUF is one which has no noise. Now, PUFs has a large body of research already. The first message I want to give is that these ideal PUFs don't exist. In reality, you see many different variations. I'm going to show only one, and that's what's called the SRAM PUF. And the SRAM shows process variability. Basically, what you have is you have an SRAM memory on a chip, and when you power it up, then the values in the SRAM going to be statistically distribution between zeros and ones. And which one will be chosen will be pure depend on the process variations of this implementation of this SRAM. And if you look carefully, the black bits are a storage of a 0, the white spots are a storage of a 1, and some are gray, which means that sometimes they power up as 0, sometimes they power up as 1, and that's actually the noisy bits. Now, what we want to do is actually we want to figure out if our devices have PUF behavior, because then we could actually intrinsically derive a key which then can be used for different purposes. Here you see an example of an SRAM of two SRAMs from two different microcontrollers. The top one is a PIC microcontroller. The bottom one is an ST microcontroller. Just visually, you see that there is already lots of correlation in this processor. So there is probably not enough entropy to derive a key in this SRAM compared to this one. And also, if you look at the statistics, you will see that this is happening. And you see that the Hamming distance between two processors is close to 50% in this case. That's what we want, but it's only 20% here. This first peaks here is within class. This is multiple readings of the same SRAM, and this is actually an indication of the noise level. So within class, we want this to be 0. Between class, we want this to be 50%. And the same is actually visible here. The lower this floor is, the less noisy your responses will be. So now, based on this one puff reading, we still don't have a key. And that's actually another body of knowledge that exists, which lots of literature available, is that once you have a physically unclonable function with a certain intra-distance and inter-distance performance numbers, you need to still derive a cryptographic key, which is perfectly uniform, he has 0 noise, and this path is called a puff-based key generation. Now this further details you can also find in the document. And the last component I want to see, which is a root of trust for many applications, which is used for side-channel countermeasures, which is used in security protocols, which is used to generate keys, and so on, is a true random number generator. Now, true random number generators are an essential root of trust in all of these applications. And you can see that it's not just a block that generates entropy. No, there is standards like the AS31 and NIST, which define which properties your random number generator should have. And you see many components here, and you have the source, you have the actual entropy extractor, you have some post-processing, and then these numbers can be used in an application. Now, on the generation of these random numbers, you have several types of testing. You have entropy source testing, you have online testing, you might have prototype evaluation. Now here, recently, there is a lot of body of knowledge has appeared on these types of testing. Because it's a challenge in an IoT device. When you generate randomness, how do you test that it's random? You cannot collect millions of bits of data on an IoT device to decide then yes or no this was random. So you have to do it on the fly. So this online test generation is a challenge. One example you see here, and after my presentation there will be a short video where you can see this in actually operation. So how do I figure out that my random numbers are really random? What I can do is I collect data, random numbers, under normal operation and under attack. And then I have to select the right statistical features to figure out which ones can detect this attack. So if this is the normal operation, I'm going to decide a lower bound and an upper bound, and from that, if I deviate from this operation, I can actually figure out that this device was under attack. So for these, you have to make hardware implementations and do some verifications. Here will fit the video, or we can see the video after the presentation. This brings me to the end of my presentation. For this hardware security body of knowledge, you should remember the most important things is that a root of trust is a component at a lower abstraction layer upon which the system relies for its security. And we have, during this presentation, identified many layers of abstraction. And so if you make a design, you have to check what are the abstraction layers, what are the root of trust I rely upon. So the root of trust is indeed one layer down, and then the weakest links overall will still decide the security. So over all your levels of abstraction, you have to optimize for security, you optimize for energy, and you have to remember that if you forget one, that's the link that the attacker might use to abuse your system. Thank you for your presentation.